Okay, as I told you, very shortly now, I will repeat some elements of the idea of the PSO, and then we will reconsider again what we did the last time. Basically, we started with the basic software. Okay, yeah. For instance, why is this presentation so strange? Let me see again. Okay, we can proceed with this. I don't know why I don't see here the picture. It's extremely strange, this. Because last time worked, now it doesn't work anymore. Okay, let me close. No, 1 second, 1 second. Let me close the presentation. Let me reopen again, because I don't know why it is not possible to see the picture. Basically, I would like to comment again the pictures. Okay, let me see. Here. Now it's blocked again. Uh, blocked, excuse me. It doesn't work. Wait again. Totally blocked this computer. This, I don't know why. Now why does strange? I don't know what I can do now. Just a second. I hope that I can open the file. It's totally blocked. The alternative is to stop everything to restart, but I don't understand.
The file on my study at least works for me. Maybe you can re-download it and try again.
But the problem is Zoom, I think. It is not able to open. Okay, probably now. Let me see. Thank you, nevertheless, for your indication. Now, let me see if it is possible. I share. Okay. Let me see if you see the picture. I think so now. I think so. You see the picture. Okay. Look, here's the example was the robot. The idea was to find velocities. If you remember, we have two kind of velocities. Let me say in a translation velocity, at least we can classify in translation velocity, left and right, ahead and the back, in this sense. It depends how many dimensions we are considering the robot, but this technical or robotic details is not at this moment relevant. And then this rotational velocity, of the end effector in order to obtain the surface or the workpiece with a minimal roughness. Basically, we have to find two elements important for us: velocity, rotational velocity, and translation velocity, in order to minimize this cost function, the roughness. Do you remember I told you about what is a non-convex optimization problem? And what is a convex optimization problem? Of course, a convex optimization problem is a problem, optimization, of course, in which we have just one minimum or one maximum. It seems to be in this picture that we have one minimum, just one minimum and one maximum. Please use a little bit fantasies. Now, it seems to be here that the surface go away. If it go away, the problem is not convex, no? Because it could be that we have a, not could be, if you go away, nevertheless, we don't have. Go away in the sense somewhere we have, it seems to be another minimum. No? But try to think that we have just one minimum, just one maximum. In this sense, the problem is convex in terms of minimum or in terms of maximum. We can also say, similar, do some consideration, similar consideration, considering flexes, no? Or a saddle point. If you have just one saddle point, this means we have an intersection. I don't know if you remember from math, no? Between minimum and maximum. No? This means it's also possible to build an algorithm which find directly this saddle point. One element. When we are looking for one element, could be a minimum, could be a maximum, could be a flex. Yeah, I think I summarize in a few words everything about this general aspects. Yeah, in case this is the most important. Why don't animate? Okay, now we can see the animation. In case we have a non-convex problem, and this is the most important application in PSO. Last time I told you a lot about that. I will come back a little bit later with the software. In case we have a non-convex optimization problem in which we have more than one minimum, for instance, no? We have many minima or equivalent many maxima or many flexes. It doesn't matter which kind of extreme we are looking for. No? Do you remember last time I told you an optimization problem in terms of minimum? I would like to say almost always can be reformulated in terms of maximum. Yeah. Yeah. And if you consider one divided, if it is possible, no? Because we have to, when we do one divided, no? We have to avoid singularity, but very often it is possible to convert the minimum as a maximum. It doesn't matter how we can optimize. Very important to find the optimal. I will come back on this. Now it's blocked, but I don't want to repeat everything. In any case, we have a population of particles which moves, population of particles which moves on my domain, the search domain, in order to find a possible minimum or maximum. Again, here in this, the upper part of the picture is easy to comment. No, we have a possible. It doesn't work. I know. When a possible cost function to be minimized, for instance, as a function of two variables. If you think about the example, translational velocity, rotational velocity, we have x and y. In x we have the translational, and in y the rotational velocity, of course. We can find the combination of two velocities in order to control the robot, to find the minimal of this function here. Yeah, and we can see the particle which is moving on the domain to find possibly the global minimum. And here's the representation. Remember, I told you about these level curves. I don't have time to repeat, but basically we reflect, I would like to say, in 2 dimensions what we have in 3 dimensions. Basically, these lines are quoted. We have the level of this line. You can figure out what is not written, the number, the quote, because otherwise it's too full, the picture. But last time with the lateral camera, I showed you what I intended with the level curves. Basically, we can really figure out if we are in the presence of the valley, let me say so, or if we have the presence of the hill, and the level of the hill, the level of the valley, yeah, we can say. Now, let me together again explain this basic 2 equations, and then we will switch directly in MATLAB. The software, I think I uploaded the software. I don't remember if it's there. We will look together in MATLAB in my study, but I think the software is there. Yeah. The second equation, before commenting again these 2 equations, let me read this sentence, let me say, in the middle. We can see that we are speaking about a matrix X. In fact, fix the idea. This worm is represented in math, in this context in the context of the algorithm, I would like to say, as a matrix. But makes sense, because in this worm is in a group, let me say, of let me say elements, bird, everything which we can imagine with your fantasy. And of course, we can imagine that I can organize, or I can represent this group of elements in a matrix. Why not? So we have a little bit a structured organization of this swarm. What is the meaning? We have row and columns, rows and columns. This means we have the coordinate of each element. Very important, because if you look at the animation, at the end, the idea is to find where is the minimum, for instance, and where means coordinate. In this case, it's easy to see or represent because we have just 2 dimensions. The problem, we say, is in 2 dimensions. Now, about the matrix, we can see exactly in this sentence that we have, again, rows and column. Basically, we have n capitalized in this notation. Sometimes it's n not capitalized, rows, and D, capitalized in this case, columns. What is the meaning? Very important, fix the idea. Matrix is clear from last time, today I repeat it. N is the number of birds, of particles. Here it is difficult to enumerate the particle because it's moving, but I can use also one particle. One particle is in a particular application, but can be used. 2 particle makes also sense. No? Basically, 2 particle means the swarm consists of 2 rows. With 1 particle consists of 1, just with 1. Can be used, but I have to clarify a little bit the meaning of 1 particle. Anyway, particles or element which is dedicated to the search, the particles moves, we can see here in the picture, is represented through the rows, we can say so, of matrix X. D is the dimension of the column, which represent the dimension of the problem. In some books, we say that the dimension of the problem is the dimension of the matrix. we can say also so, because this worm, as I told you, is characterized by rows and columns. In other literature, we say that the column gives the dimension of the problem, in the sense that we are looking for a minimum for a problem in 2 dimensions, x and y, translational and rotational velocity, as you want. I would like to say the dimensions of the matrix generate the dimension of the problem, but you can find also the different nomenclature. Second equation is easy to be commented, because again, now we know that X is in a matrix. This means it's characterized by X rows and Y column, or the better to say the pedix I and J, we can see here, is there to define the dimension, let me say so, of the optimization problem, but also to localize, please pay attention, each particle. We will see in detail what I intend. The position of each particle. We will see probably better with the software. The index, k plus 1 on the left, k on the left and k plus 1 on the left for v, which I will comment in 1 minute, states this k, the step. About the step, last time we started, but again, I started to clarify. Again, the step is quite clear if you look at the picture, which is the moving elements, because we will see that the particle will move over time. The time is the step. The time is the step of the algorithm. No, the algorithm is characterized by step 1, step 2. It's step organized. The time in the algorithm is step organized. But in any case, we can translate this step algorithm in terms of real time, seconds, hours. I show you. I already told you last time with this TikTok element. Yeah. What about V? V is not a matrix. In general, the second equation states how this swarm moves. How this swarm moves. We can see that the new position of the swarm, basically the new matrix, which states the position of the swarm, the position of each particle, is or that equals the old one. Old, why is old? Because K is the step before. If I consider K plus 1, K plus 1 is the step, let me say today, or now, and K is the step before. This means the new swarm position equals the last plus an updated matrix. Let me say now matrix, because it's the matrix V, which is characterized by I and J. Now V is a little bit. Let me say it seems to be a little bit complicated. Basically, is a velocity or a pseudo velocity. If you look at the second equation, if I multiply V by step, is exactly the velocity. Step is without dimension, no? In the context of the algorithm. This means the second equation is a pseudo movement in which I can see that V is the velocity, because the velocity is the position of today minus the position of yesterday divided 1 day. If we are speaking about concrete physical velocity, here the velocity is a little bit, we say in the literature, meta-heuristic velocity, because it's inside an algorithm, which the time, we can translate everything in time, I will tell you, but basically we have steps. And the step is without dimension. But if you think that the step can be expressed in time, of course, V is the velocity. Because if you read this expression here in this form, xi comma j k plus 1 minus xi comma j k divided the step, which is conceptual in time, or can be seen as in possible time. V is the velocity. This means it's the updated position. Yeah? If I consider V multiply by step, one step, and V is really a velocity. But anyway, speak about matrices is more abstract in the sense. Look, this expression here, I will come back on this with the software, says how I can update the matrix V. Because we can see that the matrix Vk plus 1 isn't a function of the past velocity multiplied by W. We will see that W is a weighting or a weight parameter, which can be also adaptive. The meaning is that the actual velocity, k plus 1, depends on the past. But depending very often, depending on the step, we can weight more or less the past information about the velocity. We will see the importance of this commenting the software. The other two elements, this here and this here, is a little bit complex to be expressed. Therefore, I will repeat now, and then we will see in detail with the software. K1 and K2 are two parameters which can be also adaptive. Before going ahead, I will tell you why W, K1, and K2 can be also adaptive. In the lecture of today, I will tell you just about a possibility to adapt W. In the project, we can go in depth together for possible adaptation of K1 and K2. Very shortly, the adaptation means, you remember last time I told you, two phases are important in the context of the PSO. Exploration. Exploration is, let me say, roughly speaking, the initial part of the search. Look here. Now, when we are looking everywhere, what is the meaning everywhere? It's not really very well defined. What is the meaning of everywhere? When stopped the exploration phase and when start the exploitation? Exploitation, when we are looking for what is the best, for instance, between two possible minima. Yeah. This is a big problem. It's a big problem. I will tell you a little bit, but not much. We will discuss if you choose to work with the PSO. In any case, the balance between exploration and exploitation is extremely important in the context of a possible optimization in terms of time. Because of course, if the exploration phase is too long, I need time to find the minimum. Very often in control, in particular, we don't have much time because everything runs online. This means we have to end up in one minimum, for instance. But of course, to end up in one suitable minimum, I have to explore everywhere in order to have an idea where the minimum is. Therefore, it's important this balance between exploration and exploitation. It's a big problem. Anyway, in the basic knowledge in the course, at this moment, I don't want to tell much, but I will come back on the adaptation of W. K1 and K2, we adapt in a real project. We do in my lab. But anyway, at this moment, in the course, typically we fix 0,5 K1 and also K2 0,5. Why that? Because R1 and R2 are two random parameters which change at each step. And the random parameter typically, but not necessarily in this variation, they have two uniform distribution. I don't know if you remember a little bit statistics. Uniform distribution means constant if you represent the distribution is constant. This means and the value is between 0 and 1. This means the the mean value is 0,5. Excuse me, probably I made a mistake. K1 and K2 equals 2, factor 2. I don't remember what I told you. Again, K1 equal K2 equal 2. But of course, could be adaptive, could be a different parameter. But typically, if you don't want to do an adaptation, because adaptation costs a little bit time, calculations on, and then which kind of adaptation is a big problem, believe me, this equilibrium or this compromise between exploration and exploitation. Why the factor 2? Because the mean value of a uniform distribution between 0, 1 and 0,5. If you want weight in the same way, with the same weight, let me say so, these two vector, we have two vector here, this vector here, and more than one vector is in a matrix. Let me say elements. This element here and this element here, of course, the weight must be 1, no? Or must be the same, not necessarily 1. But in the basic form, we have K1 multiply R2, excuse me, K2 multiply R2 equals K1 multiply R1 equal 1. In order to obtain this, we have to consider K1 and K2 equal 2. Because R1, as I told you, in this, at least in this variation of PSO, is a uniform distribution between 0 and 1. To conclude this, a few words about this, and then we will come back. There are two elements. This is the matrix. This is in a particular form, because we can see that it seems to be that the G best is in a vector, but X is in a matrix. Meaning, if you consider this, this element update at each particle, the new particle, if the new particle finds something better than before. And it could be useful probably to look at this picture here a little bit, to look at this picture here, in which we can see just one particle. We can imagine that just one particle with position x1, 0 and x2, 0, if you like. This is the initial position. And yeah, we can see W V, which is the vector before weight. V is the vector before multiplied by W, and then these two vector. Let me see what is oriented randomly. The new isn't just one particle. Just one particle is not exactly in a swarm. Just to figure out, because the swarm is not possible to be represented. In the sense that if we have a better element in the unit P best, which I have, I will update, and then I will add to this this difference. And then in this case, yeah, we have to consider the G best, which the G best basically is the best element of all element of the swarm. And this difference means that I will, if you do in MATLAB, basically this is a vector. In our case, it's a vector with two dimensions, x1 and x2. x1 and x2. I will reorient all swarm in accordance with this vector here. The meaning is each row of the matrix X is considered in this operation. This means this vector minus let me say the J, or better to say, yeah, you can see here, we have a J in our representation is J indicating x1 and x2. Each row of X is basically changed using this structure here. I will come back on this in the software. Meaning is I'll reorient all particles in accordance with the best particle, which at the step K I have. Let me see before going to MATLAB if I forgot to say something. I don't think so. I don't think so. Okay, let me now switch on MATLAB. Could be that I forget to push, but it's not so relevant at this moment because I will repeat in any case everything with MATLAB. Now very important, look at this. Tick. I don't know if somewhere we have a talk, but I can write talk somewhere in order to convert the steps of the algorithm in terms of time. Between talk, probably I canceled some, I don't remember where I can put it. You can put also alone if you want. You can convert all calculation between tick and talk in terms of time. Of course, the time depends of the microcontroller which we use in my computer, depends on the software, how optimized is the software. Also depends of the release of MATLAB. On the release, why that? Because sometimes we use some command from MATLAB, which then the old release was realized and it was not optimized or realized with the command which takes more time. This we have it to be when we publish some result in terms of time, we have to declare microcontroller, release of MATLAB, and of course, can be also improved because I can optimize the software. I am not expert about optimization of software, probably you are better than me. CLC, I think I clear in the command window. Let me see. No, I clear, I think, yeah, we can see. I clear the command window. It's a little bit slow. Clear all, close all means clear the variable which we have here in workspace. Close all, close the picture. Format long is just to represent with the maximum number of decimal the results. RNG is exactly what I told you, this random number in uniform, with an uniform distribution. Of course, we can use also different distribution. This is the basic PSO. Yeah. This F-min plot is a way to represent or to define a vector. We will see why we need this. Considering infinite dimension. Infinite dimension, of course, the maximal dimension with the computer can represent before going in overflow, of course. Now, LB and the UP. Remember, last time I told you about lower and upper bound. Very often, or better to say, yeah, very often we know more or less where the minimum is. Because, for instance, in the case of the robot, which I presented before, which I tried to explain, we know that, for instance, in a robot, our robot cannot run with 1 million round, I don't know, per minute, because we have a limitation. This means we are looking for a minimum inside our limitation. We cannot do better, even though mathematically probably the minimum is somewhere or outside of our limit. But we can look just, we can find just what we have. Of course, mathematically we are speaking about a suboptimal, but we have this robot. We cannot run more than the robot can. We can see here we are looking for a minimum between, for the variable x1, between -10 and 3. We can look at the minimum between -9 and 10. You remember last time the didactical example which I presented? The cost function to be minimized is here, output function. You have these two files in my study. Is an artificial example. Is an artificial example to clarify many things in PSO. We can see that we have two variables to be optimized. The function, I think you know what is the function. No, the function is an object, let me say, which can be called by a main program. Also, of course, I can integrate everything in one file, but didactically, I think this is easy to understand. I mean, x in this case is in a vector. We can see from here with two components, x1 and x2. This is the language of MATLAB. We can see very easily that the minimum is in a paraboloid. The minimum x1, let me say x1 equal 2 and x2 equal 3. And the value of the minimum is 100. Of course, the example a little bit strange because it seems to be that the problem which I am considering, at least in this application, is a convex problem because we have just one minimum. Yeah, but we will see, nevertheless, makes sense to analyze with the PSO, even though probably we have other methods more efficient in terms of calculation. Because you remember last time I told you that the calculation load is very high in PSO. And not only very high, increasing really drastically with the dimension of the matrix of the swarm. Nevertheless, I will tell you why sometimes also in case of convex problem, we use PSO. Last time I tried to tell you a little bit. I have also here the scheme. Yeah, I will tell you a little bit later when we try to simulate. Right. This is the problem which I want to attack. And as I told you, we can see that the minimum is 2, x1 equals 2, x2 equals 3. And if you look here, it seems to be included, no? Because 2 is inside 10 minus 10, 3, and 3 is inside minus 9, 10. Now, this of course, it seems to be that I need some a priori knowledge, but this is always possible to have an idea where the minimum is, or as I told, let me close the mail because otherwise, or as I told you, sometimes we have some physical limitation of the system with which we are working. The example of the robot makes sense. It makes sense because where is now? Yeah. If the robot does not have a limitation in velocity, I have to find the minimum inside the context of the velocity of the robot. This means it could be that mathematically is suboptimal, but I cannot do better. When defined the lower and upper bound, we can proceed. This is the initialization phase. We need lower and upper bound. If I don't know anything, mathematically, of course, I can write plus infinite minus infinite, plus infinite upper bound minus infinite lower bound. But of course, you can realize that it's not so suitable because plus infinite minus infinite doesn't make any sense. But of course, if you don't have any idea, I have to enlarge it, or at least mathematically it's possible. Mathematically possible. There is theorems which say that the probability to find a global minimum depends on the density of the particles. Depends on the density of the particle. This means if I have a large domain, I have to put a lot of particles. We can understand very well. Do you remember last time I told you, if I try to find an object in this room, I don't know, it could be that I find or I don't find, or I don't know if I find exactly what I want to find. Of course, with two people, it could be that I probably to find what I want to find, the best, it's higher. You can understand a little bit this. This means also this is an important concept of the bound. I will tell you. I don't have much time, but I will tell you a little bit also more later. But during the project, we can consider also interesting variation on this bound, rebounded, variable bounded. Anyway, we can understand that also here is a compromise. It's a compromise because if it's true or if it's valid, that the probability is intuitive, no? It's valid intuitively in any case. The probability to find the best element depends of the number of particles. It's clear that it's valid. The example, if I want to find something here in the room, could be useful to look at this something with more than one people. But also more elements means a lot of calculation load, because I don't want to give you some mathematical indication, but just to roughly speaking, the calculation load increased drastically with the dimension of the matrix in general, not only of the column, but in particular, but also, let me say more precisely, on the rows, which reflect the number of particles. M2 is the number of variables, x1 and x2. And exactly what I told you until now is the population size, the number of particles, birds, which is moving, the particles which are moving. Yeah, and sometimes n capitalized. But anyway, now I use this notation here. Look at this. Do you remember I told you the weight on W? We can see here the maximum 0.9, the minimum 0.4. About the value, we can choose also different value. There is literature, what is the best, but of course, it's a little bit arbitrarily. This is the typical choice. I don't want to go in depth on this technical. Let me go in the concept, because yeah, as I told you, C equal to, but could be also adaptive. We typically use adaptive in our project. In the project I can go a little bit more in depth when we do the project, how we can, let me say, improve, because adaptive costs energy in terms of calculation, but typically is working better. But anyway, also fix it's a possible variation, because we say we can avoid a lot of calculation, and of course we are happy what we find in this sense. Yeah, intermediate iteration. I didn't use in this lecture, but you can understand that sometimes it's useful to check a little bit what happens during the iteration in order to stop the algorithm. If we have a necessity to stop. In control, very often we have. This also is something which I will tell you eventually. This is important, nevertheless, in the project, because I don't want to do this lecture extremely complex. It's not so difficult, but I try to conceptualize more. There is the possibility to check intermediate. Intermediate means we can see what an 800, we can choose this with respect to 1000. The meaning is the maximal iteration in 1000. It could be that we would like to check also earlier. Sometimes we do, I have also here an adaptive check. I tell you in a few minutes. This means we don't have to wait the maximal iteration. In control, we don't wait this. It could be that we needed to check a little bit earlier. I will tell you a little bit, but it's not implemented, but the implementation is extremely easy. This max run loops equal 1 also is not implemented in this lecture, but it's also easy to do, because sometimes we can work parallelly with more than one swarm. Didactically, I put one because I don't want to also put many aspects in the program aspects. It's not really extremely important, this aspect here, but try to consider that we can have many variation of the basic software, or the basic structure of the algorithm. Also, this is related to, we can see here, no? more swarm in parallel. I don't want to tell you. Also this one, no? Because it's related to this possibility to work with more swarm in parallel. Forget this, because it's just a possible variation, which if you want, we can apply in the project. But let me go ahead with the concept. Now, initialization phase, again, we can see this loop which we are running now. Here again, this is not active because the maximal loop is 1. We are working with just one swarm. Look at this 2, 4. This 2, 4 is here to fill up my search domain with the particle. We can see that here we have a matrix. I don't know if you remember MATLAB language. No, we have a matrix characterized by x0. 0 means initialization. No? We can see that we try to fill up in terms of x and y, basically in all the whole matrix between LB lower bound and upper bound of what? If you look at this expression, we try randomly. This is a way to say at each step of the 4 of the in this case put what a number, a random number between 0 and 1. I already told you that we defined we're working with this assumption. Basically I add to the lower bound what randomly this element here. This means it's easy to see that we are moving between lower and upper bound in a random form. I mean, for random equals 0, we are exactly on the lower bound. But I think 0 in excluded. 0 in excluded. Because this random, if I remember well, is between 0 and 1, but excluding the extreme. This means 0 plus epsilon and 1 minus epsilon, if I remember well. But anyway, it's irrelevant. We can check. We can see that if it's 0, we are, let me say, on the lower bound. If it's 1, we are on the upper bound. This means randomly, I fill up my swarm with particle with the position between lower and upper bound. Easy to see. I don't remember this random, but could be that's also included. It could be. I don't remember. We can check if random include also the extreme. It could be. I don't remember. Look help rand. But in any case, the concept is I fill up without any other issue. I change name, no problem. Also, this is an assumption to say that the initial V vector matrix, the matrix of the velocity, you remember I told you, is 10% of the of the position. So we can use also a different value. Also, this is really arbitrary in the sense. Anyway, we have to start also with the matrix 0. I already told you how we can do randomly, and then I will start with the matrix V. In other variation, they randomize also V, but it's not necessary because x0 is already randomized. Now, always initially phase. Look, very important this. If you remember, output function is exactly the name of the function. Look here. This file here, the name is output function, is also the same name of the function, but very important, the name of the M file. Meaning, with this command here, I will call, this is the name of the M file, which is the same of the name of the function. Means I call the M file and I calculate the M file, which is in a function, at this word. In fact, at each I, at each particle, and for each, better to say for each row, because this MATLAB command means these columns this column, means I will consider for each I all column. This means I will check at each particle the value of my function. Basically, you can think about this worm that each particle is characterized by two, in this case, two coordinates, x1 and x2. This is the meaning. This means at each particle, which is characterized by all column, x1 and x2, calculate the function. The function was this one. No? I put the value of my random x1, I put the value of my random x2, and I do this calculation. And I save the calculation, we can see, in one row each time. Of course, each time, each I. Basically, F basically is in a, is in a column, no? F null, F0 is in a column. I made mistakes. F0 is in a column because I fix the second variable. Is a column in which I save the value of the function, cost function, calculated at each particle I. It's a little bit complex, but it's easy to see. Now, look, this is easy. I calculate min if I look min. If I want to calculate max, is not our case. I have to write max. Therefore, I told you the real calculation time depends also of the release of MATLAB, because sometimes they improve this command min. Anyway, command min probably no, because it's already done. But anyway, if you use some different command inside the program, it could be that between the release they change or they improve or I don't know what. But let me go ahead with the concept. This means look on this column, what is the minimum, and save the value of the minimum and its coordinate. Coordinate means which particle found the minimum, which is the best, and where is the best and its value. No? This is where is the best. Where is the best is the particle. Particle number one, particle number two. But why I'm saying where? Because the particle is characterized also by x1 and x2. Anyway, we have really the position in this worm, I would like to conclude so, of the minimum, and also its value. Its value is this one. I mean, if let me say, if the minimum is in the second particle, the second particle is characterized by the matrix 0 by x1 and x2. This means I know everything. Let me see if I forgot something to say. Because x0 contains all information. If I know where is who is the particle number 2, I know also its coordinate. I can understand better the problem. Look, I put in P best. Now it's just in a position, x0, just in a position, this moment. Here is in a position, but more conceptually, because look, I write in G best the best particle with its coordinate. This was number 2, which is characterized by x1 and x2. In x null, do you remember I told you exactly? Because x null has the information of all possible information which we need in the context of this worm, of course. This means in GBest I save, we can see the best particle. I mean, P-best is in a matrix, just change name. G-best is in a vector. We can see here because I am considering all coordinates. iteration 1 because I need to start with the iteration now. Tolerance I didn't apply in this variation because I don't want to tell you a lot, but you can see here I can organize and stop criteria and control is important. We can do together in project, but it's really easy to do. Now we fly. Huh? The initialization phase is ready here, which we have. Once I initialize the swarm, we have the best bird, the best particle, and we have the position of the swarm in p-best. Therefore, we are the end of the the initialization. Therefore, I define the iteration. We can see here while iteration, because at the end I will increase this variable iteration. While iteration less or equals maximal iteration, run what we have between while and its end. I don't know if you remember a little bit programming in the sense. No? Of course, I can stop earlier with different criteria, but I didn't implement here because otherwise too many information. Look here, W Vmax minus Vmax multiply Vmin, we defined, remember this, no? Multiply iteration divided maximum iteration. If you look at this way to proceed in the native form, we can see that at the beginning, when the iteration is equal 1, we are almost in Vmax. Why that? Because this is almost 0, no 1. This means remain just this. Therefore, I told you almost in more or less in Vmax. Increasing iteration, when iteration equal maximal iteration, we have in Vmin, meaning that through is in a way, this is way to wait, not the unique one. In this sense, what is the meaning? We trust the PSO in the sense at the beginning we go far away, we try to emphasize the exploration, and then we try to converge during the iteration. Of course, I don't want to go in depth on this because it's a really complicated structure, but the idea is easy. You know, at the beginning, look everywhere. V, the old V is weighted stronger, and then we converge because V is smaller and smaller. This means these three vectors collapsing into. Here, in these two, let me say, loops, we implemented, we can see here the V. Then I spend a little bit the energy here to clarify. Again, this is changing between and a small value, big value 0.9, could be also 1, and 0.4 could be also different. This is really arbitrary very often. Here is exactly what I told you, these two elements, Here is the difference between two matrices. Of course, at the beginning it's 0, no? Because as I told you, x equal x0, and I put x0 equal this one. But we will see in the second step a change also. I mean, PB best is not equal x. The meaning of this, I'll replace, or yeah, in P best we will see that we have the new value of the particle for each particle. I will reconsider the best, such that I will, let me say, reorient somehow the whole swarm. The whole swarm, of course, can be done as also in a different way. It can be done in a different way. Sometimes also without this component, about this variation, we can talk together in the project. Sometimes we have just this one and this. This is more clear the meaning, because at each we consider different between the best particle and each row of the past swarm. Basically, we reorient each particle in accordance with the best one, because it seems to be not possible to do, but because, look, here's a vector. For each j, we have a vector. I don't know if you remember this. In a row vector. This was in a row vector. We define. No, this is a little bit difficult to remember. Where is it? Yeah. Is in a row vector. This means MATLAB understands this calculation for my row vector. We subtract at its component. The internal loop is in fact J, but it's in a row. This is easy to see. This I will reorient somehow each particle in accordance with the best one. Of course, we have also the variation without this, no? Without this, just with the p best. Because nevertheless, the search would work. But of course, this possible choice in which we consider both component is in a mix again. I don't want to go in depth between exploration and exploitation. I mean, this component here, given a direct contribution, more direct contribution exploration, because we consider every element. I mean, the global, better to say, the global world. Here is more oriented to the exploration, because we orient each element considering the best. Of course, we can see that everything is a little bit arbitrarily, because we can also proceed in different way. How we can is the best. Sometimes we have to test. I would like to say we have, in fact, variation without this. The name is anarchy, because here GBest is the chef, is the best. Or we have also variation without this. This means just with the chef, or sometimes with more than one chef, more than GBest. Let me go ahead, because in this 10 minutes I would like to conclude. And next week, nevertheless, we will repeat a little bit. I will show you in a real example, and then we will go ahead. Here is the second equation. We can see again two loops. Once we have a V, as I told you with the slide, we can reconsider the new X in accordance with this. Of course, we have also different variations. Then these two loops together, three loops, and if you consider the if, I check if the value with the minimum is in the lower bound. If in the lower bound, we have some problems. I will discuss also this problem also next week. We have some problem because this means I can draw this a little bit to view what it means. That minimum, or at least PSO, sees a minimum outside of the boundaries. Look. Okay. Okay, let me move a little bit here. Let's move. Just to understand what happens in the boundary. Let me see, let me say this is the minimum which we're looking for. Let me see that erroneously, or anyway, we fix the lower and the upper bound in this form. I can test also with you. It's clear. It could be in at least in case of convex necessary. I show you exactly with example. The PSO will found this because you see that the minimum in somewhere outside. Let me do a little bit better. Now, no? Here's the minimum and the lower bound and upper bound. Of course, this is not acceptable, or yeah, we can also accept this one if we are fixed yeah, inside the lower and the upper bound in this form. Very often, yeah, yeah, we have to, we have to know if at least if we have just one minimum, we have to know. But of course, if we cannot do differently, we can accept this one. But PSO says to us that at least the mathematical minimum is outside on the lower upper bound. About that, we will discuss a little bit, also go in depth next week. Let me finish now. I don't need much now. Why it doesn't work? The problem of the Zoom is in. I cannot change now the problem is Zoom. Let me come back here. One second. Okay. I cannot come back to MATLAB. I don't know why. Did you see MATLAB? No, no. No, I think so. I hope this Zoom is this. You should see MATLAB, I hope. Yeah. Now look, what I am doing is exactly what I did in the initialization phase. Now I have a new position of this word. I look, I calculate before looking, I calculate the function at the new position. X I semicolon is the new position. Updated. Of course, it could be that I have some element of the lower or the upper bound. That it could be. And then what I do, please pay attention to the last element. Not exactly the last. We have just two things to clarify. I will check. Now, F0, F is the new, excuse me, is the new calculated value of the function. Now, if we can see here, the new calculated value is less than the old one. That is the old one. I would like to say the old one at the beginning is just the initialization. I put what is better. Why that? Because I'm looking for the minimum. In this case, if the new value is better than the initialization, I will put in the p-best. Basically, I will re-update somehow this word. And very important, I put the new one in F0 because now F0 I will use for the next step. At the beginning, the step 1, F0 is the initialization. But then for the next step, I have to compare what I find at the step 2, let me say, in order to understand, with F0, which thanks to this sentence is the new, it is the element at the step 1. I calculate the minimum of F0, which is the new, let me say, the step 1 in our case. I fix where is, which particle, and the value of the minimum. I don't have to explain this best iteration because it's related to the more than one loop. What I am doing now, easy, because if F min, the best of the best, is less than F min 0, F min 0 was exactly, do you remember the G best, where I define F min 0 at the beginning, not to understand. I have to, yeah, the beginning. In the initialization phase. I am analyzing the step number 1 this moment, just to understand, to clarify what I am doing. I put, if this happens, the best of the P best, the best of the P best, because it's here. When happens, the best of the P best in G P best, and very important, the new best element in F min 0, because I have to do at each step. This is a step number 1 in order to understand, and the step number 2 I have to update it in order to do the correct comparison. Therefore, I will reuse this somehow, but it's the new one as here. It's the same concept as here, which I put here in order to reuse each time the best at each time. We are ready? Yes. Here I don't have to comment this because we don't use this iteration. The tolerance, of course, I don't use in the software because otherwise it's too much to explain. I plot the value each time, where basically where the minimum is, and the value of the minimum we can see here. Of course, we can also optimize this. We can recall the function. We can do many things. Let me run, and then next week is running. We can see value x1 equals 2, value equals 3, the value is 100. Let me change here just to understand. If I put 1, now the value 2 is outside of the boundary. Look what happens. I am on the boundary because the PSO sees that the minimum is in 2, but we are limited. Let me restart another test, and then I will conclude. Next week, we will go in a little bit in depth in the first part of the lecture. It could be that I dedicate again another lecture, depends, because I would like to tell you many things. But at the beginning, I know for students who didn't see, this is a little bit difficult. Let me run now again. One second, I am concluding. No? Let me copy this. Let me do another change we will discuss next week. But a little bit I would like to discuss also today, but shortly. Let me reduce the number. 10. Look now. Look. Yeah, we don't have many differences. Let me, because probably the dimension of the problem is too small. But now we can see that you have a larger error. Larger error. It's not exactly 100. It's not exactly 2 and 3. Or the error is larger than before. No? I can do next week a little bit better, including also more dimension, x1, x2, x3. The concept of the density is the concept of the density, but it's connected with an important problem, which I sketch now, and then I will conclude. 1 minute really, but next week we will. Mathematically, we have something like that. No? In one dimension, of course, in two dimensions, it's a bit more difficult to draw, but the concept is the same. If I have a more dimension, this problem is more important because you remember the concept of the density, no? The density of the particle. This is mathematically what we have, but practically, because we are working with the computer, we have something like that. This means it could be, now is a little bit strange, it could be that we will stop, not exactly in the minimum, but close to the minimum. This means also in a convex problem, because of the discrete representation, makes sense to use PSO, and not necessarily a tangent-based or gradient-based method, and to use an enough number of particles. We have seen in this simulation. Next week, we will restart with this concept here. Here is not so visible because the dimension is very, very small, 2 elements, but nevertheless visible. Far away from 2 and 3, more far away than before when we have a lot of, we have a 10. Yeah, we can see definitively without calculation, we can see directly. Okay, this concept and other concept I will clarify a little bit better next week. I will tell you about in a practical, in a real application with the software I will upload. I don't know if I uploaded last time. It's not so difficult. Then we improved also for the project. But in any case, next week we will conclude with the PSO. It could be that I need the full lecture, and then we will attack another topic in this sense. Questions? If no questions, we will see again next time just in Zoom. No, I am not in Lunarboard because I have the permission to be here. But the lecture is nevertheless just in Zoom. Any question, you can also contact me anytime. But anyway, in this first phase, I can understand that is oriented, is an orientation phase on PSO in particular for this session here. Okay, I stop the